So, welcome to chapter 6, Pressure and the Fluids. Now, this chapter is even more important in the medical field because pressure affects many parts of the human body. The blood pressure in the heart, the pressure in the urinary bladder, and the pressure in the eye are just a few examples. We know that any abnormal changes in pressure will affect the body. Blood pressure is a primary example. Now, in the eye, again, there are fluids that cause the pressure, and if the pressure becomes abnormal, becomes higher than a critical value, then it can even damage the optic nerve. Now, the urge to go is because urine fills the urinary bladder, and as more fluid fills it, the pressure increases. This sends a message to the brain, triggering the reflex to go. So you can see that as shown here. And the physical concept here is that the more the amount of fluid in the urinary bladder, in this case, the bigger the pressure. So here's the structure of the eye, and the eye contains two types of fluids, the aqueous humor and the vitreous humor, and for which the typical values of pressure are between 10 and 20 millimeters of mercury. So as we go forward in this chapter, we're going to see that there are many units for measuring pressure. One of the units is millimeters of mercury. Now, coming back to the eye, the changes in the pressures of the fluids can affect vision, as in the case of glaucoma. Cardiovascular pressure is the next chapter, which shows how important that is. But here, looking at it briefly, we know that the blood pressure indicates the health of the heart. The systolic blood pressure is when the heart contracts to pump blood, while the diastolic blood pressure is when the heart relaxes, where blood flows back into the chambers. And the typical values for systolic blood pressure is 120 millimeter mercury, while that for diastolic blood pressure is 80 millimeter mercury. So that's why we say the normal blood pressure is 120 over 80. Now, respiration is also because of changes in pressure in the lungs. We can see that during inhalation, the diaphragm moves downwards, and as it moves downwards, it reduces the pressure inside the lung, and then the lungs expand into that available space, allowing the air to flow in through the nostrils. During exhalation, the diaphragm comes back up, so there is less space for the lungs, and that increases the pressure, forcing the air out of the lungs. This is just another importance of how changes in pressure affect the human body. Hydrocephalus in children. It's a condition characterized by an excess of cerebrospinal fluid within the cavities of the brain. That's when the flow rate is affected and it collects around the brain and spinal cord before it gets absorbed into the bloodstream. So here we have extra pressure on the brain, which can lead to very harmful effects. So here various values of the pressure are given. You can see that the systolic pressure in an adult could be between 100 and 140, again, millimeters of mercury. But for infants, it's between 60 and 70. Diastolic is between 60 and 90 for adults, 30 and 40, between 30 and 40 for infants. We see the blood pressures in the veins, in the arteries, in the bladder, 0 to 25, and then in the brain, 5 to 12, in the eye, the gastrointestinal pressure, the pressure in the middle ears, very small, less than 1. Now, all of these units are in millimeters of mercury. So what is pressure? How is pressure defined? This is where the physical concept comes in. Pressure is the force acting over a particular area. So to get the pressure, we got to divide the force with the area. Now the force is in newtons, while the area is in meters square. So those are the proper units, Newton and meter square. Therefore, the unit of pressure is just Newton divided by meter square. Newton per meter squared, that's what we call it. It's also called Pascal. The symbol is PA. So you can either write Newton per meter squared or PA. So when you look at this equation, it's very clear that if the area of contact becomes less, then the pressure becomes bigger. They are inversely proportional. There are many examples for this. This is why we need sharp knives. So when you say that a knife is sharp, you actually mean that the area of the cutting edge is very small. And the reason is a smaller area leads to a bigger pressure. Another example is we are able to push a thumbtack into a piece of soft wood easily. Now where you're applying the pressure, that part, the area is much bigger than the pointed tip which goes into the wood. So it's the same force acting at both ends of the thumbtack, but the pressures are not the same. Where you're applying the force, the area is bigger, so the pressure is smaller. That's why it doesn't hurt you. But at the other end, the area is small, therefore the pressure is huge and it goes easily into the wood. Or I hope that makes sense. And so here is a question. As a woman walks, her entire weight is momentarily supported on the heel of one shoe. She's standing on one leg now. Calculate the pressure exerted on the floor by a high-heeled shoe worn by a 50-kilogram woman. Now, if the heel has an area of 2.00 centimeters square, see, the area is given in the wrong units. Express the pressure in newtons per square meter and atmospheres. Okay, so force. The 50 kilogram is not force. The 50 kilogram is the mass, M. Now to convert mass into weight, we have to multiply it with the acceleration due to gravity. Weight is the force. Okay, so kilogram is not force. Multiplied with 9.8 meter per second squared, it becomes force. So that's what is done here. So 50 times 9.8 gives 490 newtons. Now the area in centimeter square to be changed into meter square. We know that 1 meter is 100 centimeter, but we got to write it twice so that it cancels out, because otherwise it won't cancel. See, now because you have written it twice, you can cancel this centimeter and this centimeter with this centimeter square. So now it works, and you get it as 2.00 times 10 to the negative 4. Because in the denominator you have 1, 2, 3, 4. So that is 10 raised to 4 in the denominator. So when you write it on the top, you got to put 10 raised to negative 4. So now we have the 4s and the area. All we got to do is divide them. When you divide them, you get 245 times 10 raised to 4 Newton per meter square. Now that's the answer in Newton per meter squared, and we need to change it into atmospheres. So we're going to talk about atmospheric pressure later on, but right here just know that 1 atm is equal to 1.013 times 10 to the 5. So you see that number. So you got to know that. So if you divide Newton per meter squared with that number, you get it in atmospheres, or ATM. Okay, so that is the problem there. Now let us think about pressure applied by fluids. Now a fluid can be a liquid or a gas. Anything that flows is a fluid. But here we are basically focused on liquids. Now the pressure exerted by a fluid depends on chiefly two quantities. Number one, the density of the fluid. The density here is represented with the Greek letter rho, R-H-O. So that's one quantity, and the other is the height of the liquid. So in this container, you have liquid up to this height. You can see if you had more liquid to a greater height, then there would be a bigger pressure. Okay, so now the pressure exerted by a fluid is rho times G times H. Rho is the density, must be in kilogram per meter cube, and H is either, call it the height or the depth. If you're measuring it from down up to the bottom, you call it the depth. So you can call it the depth. Okay. So pressure increases with the depth. You see that the pressure exerted by a fluid increases with depth. That's obviously because if you have more fluid, then you have a greater weight acting on top, pressing down on the layers below. All right. Let's use this equation and calculate the pressure in the Marianas Trench, which is near the Philippines. That's the deepest part of the Pacific Ocean, or actually any ocean on the earth. And the pressure is going to be high. We're going to calculate it. The depth is 11.0 kilometers. Now we can't use kilometers, so you got to change that into meters. And the density of ocean water is slightly more than that of water. Water would be 1,000 kilogram per meter cube because it has dissolved salts in it. That's why it's 1,025. So now first change the height from kilometers into meter. You know that 1,000 meters is 1 kilometer, so that's 11,000 meters right there. And then the formula is rho GH, plug it into the formula. So that's the density times 9.8 meter per second squared. That's G, and times the height. When you multiply those three, you get a big number, but putting it in the scientific notation, you see the decimal is here, so take it back 1, 2, 3, 4, 5, 6, 7, 8 places. So that's 1.10 times 10 to the 8 Newton per meter square. That's the pressure exerted by just the water in the ocean. That is not the total pressure. We will calculate the total pressure just a bit later. Okay. So here's a container with 3 holes made at different depths, and it's very clear that as the depth increases, the pressure increases, therefore it shoots out with a bigger velocity. When it comes out, the velocity is bigger, so it goes further. So that is very clear. But what is interesting with this container is that the quantity of liquid in these containers is not the same. So this one should have the lowest amount of liquid. Their shapes are not the same. The quantity of liquid is not the same. But believe it or not, the pressure at the bottom of the containers is exactly the same. Look at the gauges. They're all reading the same pressure. Why? Because it only depends on the density. If the liquid is the same, then you have the same density G and H. So it only depends on the height and the type of liquid. As long as this is the same liquid, like either water in all the 4 or any other liquid, as long as the liquid is the same and the height is the same, no matter how much fluid you have or what the shape of the container is, doesn't matter. The pressure exerted will be the same. All right, now we come to the atmospheric pressure. You can see in this diagram that the atmosphere is divided into so many regions. You have the troposphere, stratosphere, and all that. So that's huge. And all of this air is exerting a pressure on the surface of the earth. And that is called the atmospheric pressure. And this is a big number. This is called 1 atm and should not have been caps. It should be small letters, atm. And important to know, we use this once, that 1 atm is 1.013 times 10 raised to 5 Newton per meter squared. So whenever you calculate I should say when you measure the pressure using a gauge, like when you're trying to measure the tire pressure using a tire gauge, the pressure that the gauge shows us is not the total pressure. It's only the pressure in the tires over and above the atmospheric pressure. So if you want to get the total pressure, we got to add the atmospheric pressure to the gauge pressure. Let me say that again. To get the total pressure, you got to add the atmospheric pressure to the gauge pressure. Now the total pressure is sometimes called the absolute pressure. So it's either the total pressure or the absolute pressure. So the previous problem that we worked out, we had this as the pressure due to the water in the ocean. Remember that? Now, if you want to define the total pressure or the absolute pressure, you would have to add the atmospheric pressure, which is here. And now adding these two numbers is tricky because here you have 10 raised to 8 and here you have 10 raised to 5. Put it in your calculator and check if you get 1.101 times 10 to the power 8. That is the total pressure. So here is an important principle called Pascal's principle, using which the brake system in a car works. I just want to say at the beginning that a fast-moving car has so much energy, but we are able to stop it by applying a gentle force. That is because of such a system. Not exactly the same shown. This is the most basic. A little bit more complicated, but builds off the same principle. So what is Pascal's principle? The principle states that the pressure at any point in a fluid at rest. So this only applies to fluids that are not flowing. The pressure at any point is the same in all directions. So at any particular height, if you look at the pressure, it'll be the same in all directions. That's what it shows. And if you increase the pressure, like when you apply a brake, if you increase the pressure in one part of the fluid, it is transmitted equally in all directions. That is obviously why when you apply that increased pressure on the brake, it goes out to all the four tires and the same pressure acts on all four, stopping all of them together. So here there is a formula which is a ratio. The force applied on the smaller, okay, first of all, you see this hydraulic press, which is a smaller cylinder connected to a bigger cylinder. That's the hydraulic press. You know what it's used for? It's used to lift heavy objects, like a car in a service station. So if you apply a small force F1 on this side where the area is A1, you're going to get a much bigger force on the other side because the area is bigger. So the idea is when you apply the force, there is a pressure which comes here. And you know, pressure is force by area. So what we did is just put the pressures to be equal. Because we know, according to Pascal's principle, that the pressures at both should be, or in both should be the same. So F1 by A1 is F2 by A2. So significance, a small force applied to a small area results in a large force. Let's work out a problem. Calculate the force that must be exerted on the master cylinder of a hydraulic system. So that's the master cylinder, the smaller one, to lift a 10,000 kilogram truck with the slave cylinder. So the slave is the bigger one. The master cylinder has a dia of 1.50 centimeters. That's the diameter. Slave has a dia of 30.0 centimeter. First off, you have to take the radius by dividing each number by 2. And then you have to calculate the area. The area of a circle is pi r squared. Pi r squared. So that's why I've first calculated the area of the smaller part, which is pi r1 squared. That's pi. And then I took half of this and then divided it by 100 to change it into meter. Okay. 0.75, that's half of this. So I divided it by 100, which is the same as multiplying it with 10 to the negative 2. So you can do it in your own way, but you have to square both these numbers, square this and square this. So when I square this, you get 10 to the negative 4. See that? So that is the area of the smaller one. Similarly, the area of the bigger one is pi r2 squared. So half of this is 15, and change that into meters, 0.15. So when you do the math, you get 0.4713 meters squared. So you got A1 and A2. And you have F2. You have 98,000 Newton. How did we get that? Remember, this is mass. You got to multiply it with 9.8 to get the force. And then plug it into this formula. I've just taken A1 to the other side. It goes to the numerator. That's a math. And then plugged in the numbers. F2 by A2. See the A2 times A1. And I get 49.0 Newton. So such a small force can be used to lift 98,000 newtons. No wonder the diagram shows somebody using a little finger. So this is how the hydraulic jack works. Like when you have a puncture to lift one side of the car, you use a hydraulic jack. It's the same exact principle. All right, except that it is a locking mechanism where you keep pushing it down in steps and this keeps going up in steps. Okay, it has a locking mechanism. So just one or two more applications. You can see that the IV fluid is flowing into the patient because there is a higher pressure here. You see that it is at a higher, it's a greater height, so the pressure is higher and so it's easily flowing into the patient. And I've written that, remember that the height above the patient is only the vertical height. We don't care about the length of this tube, it doesn't matter. So you could have had it, I don't know why, but you could have had it that way. It's only the vertical height that matters, not the length of the tube. The length of the tube does not affect it. Now, when somebody donates blood, you know that wherever you're collecting the blood should be below that, because now you want the blood to flow from the patient into the container. Okay, so here is the medicine dropper. How does it work? Well, first when you press that rubber, you're pushing all the air out, so the pressure is less now. And then keeping it pressed, you dip it into the medicine, and when you remove the force, the medicine gets sucked back in. Why? The atmospheric pressure is pushing that liquid into it because it's a low pressure region. And then if you want to, you're actually transferring it, so to take it to another part, when you reach there, press the rubber again and the fluid is forced out one more time. So that's how you could transfer. So there are a lot of simple applications where pressures are used, which many times we don't even realize. So here, there is a lot of content here about blood pressure, and how blood pressure readings have to be taken at the heart level. You cannot take it at any other place. And that is shown here, because here you see that the blood is pumped from the heart, and the pressure here at the brain should be less. Pressure at the brain or at the head is pressure at the heart minus rho GH, where H is this height. See? So for very tall people, obviously, the heart has to work more to take that blood up to the head because the height is bigger. But when you look at the feet, now it's below the heart, therefore the pressure here is going to be bigger. So the pressure there at the feet is the pressure at the heart plus rho GH. You see, one is minus, the other is plus. Okay. So the pressures are not the same at every part of the body is the significance of what I'm trying to say. Now this one, I'm not going to read it. You can take your time and read it, but I put it here to show you the importance of taking the blood pressure at the heart level. Okay? It describes the hydrostatic pressure variation due to the force of gravity. That is, the height of the measuring device relative to the heart affects the hydrostatic pressure. So you have to have it right there. Otherwise, you get false readings. And then the diagnosis will be wrong because the diagnosis is based on blood pressure readings. Okay, so you can read that and there should be some conceptual questions from there. So here is a question dealing with a syringe. A syringe has a bigger part, a bigger cylinder with the needle having a really tiny area. So the plunger on a hypodermic syringe has a dia of 1.0 centimeter. So that's the diameter here, 1.0 centimeter. I should show this as the dia. Okay. What force must be exerted on the plunger to inject medication into a vein that has a blood pressure of 10.0 millimeter mercury? So that's a typical value of pressure at a vein. So diameter is 1.0 centimeter. We got to change it into meter. So divide it by 100, because 100 centimeters make a meter, and you get that. And then there's one conversion that you have to remember, that is how to quickly change millimeters of mercury into pascals. So here in this case, 10.0 millimeter of mercury. How do you change it? You see this number is what you have to know. 133.3 pascals is equal to 1 millimeter of mercury. So I should have written, let me see, I should have written Pascal there, and I will try to write with the mouse now. Okay, so 133.3 pascals divided by 1 millimeter of mercury. So that's why you see the millimeter of mercury gets cancelled, and you have your answer in pascals, which is 1333. So that's the blood pressure at the vein. And then the area is pi r squared, because it's circular. Pi times, what is that? Well, that's because we had the diameter, and you've got to take the radius. So you got to take half of that, which is here. And then pi r squared gives you 7.85 times 10 to the negative 5. So that's what you get. 7.85 times 10 to the negative 5. So that's the area. And we're asked to find the force. Now, force is pressure multiplied by area. Yeah, because pressure is force by area, correct? Pressure is force by area. Stay there, come on. All right. Pressure is force by area, so force is pressure times area, and you get this. So that is the force that the nurse has to apply to inject the medication into the vein. Simple enough, right? All right, so we come to the last part of this chapter where we talk about the buoyant force. So if you take a solid and put it in a liquid, the weight of the solid appears to have decreased because all liquids push back up on a solid. The best example would be if you had a rock underwater. It would be much easier to lift it while it's underwater. But as soon as it comes out of water, you're going to feel its weight. Now, that means when it's underwater, the liquid is helping us by pushing back up. So that force is called the buoyant force. So you see here, the buoyant force is the force applied by a liquid on a solid submerged in it, or even partially submerged in it. So this is the scientist who got this, Archimedes. According to this Archimedes principle, if an object is completely or partially submerged in the fluid, it will experience a buoyant force. But you have to remember that that buoyant force is equal to the weight of the fluid displaced. The weight of the fluid displaced. This is obviously why huge ships are able to float in the ocean. Because although the weight of the ship is big, because of the shape, it's able to displace its own weight. So the buoyant force, important thing is, the buoyant force is equal, what is that? The buoyant force is equal to the weight of the fluid displaced. All right, the buoyant force is equal to the weight of the fluid displaced. That's the formula that's given under here. Buoyant force is weight. How do you get weight? It's mass of the fluid times 9.8. So I'm going to demonstrate that with this question. A really important and good question. So the question says a piece of iron with a mass of 1560 grams in the air is found to have an apparent mass, so it appears to be only 1402 grams in a fluid of unknown density. Okay. So we know that the buoyant force must be the difference between the two. I've actually done that here. Okay. But first the question is, find the volume of iron. Oh, we have the mass of iron. We got to find the volume of iron. So we need the density of iron, which is to be taken from this table. I've given it here. So that's the density of Fe, is the chemical symbol, atomic symbol for iron. So density of iron, 7.8 gram per centimeter cube. So we have to use consistent units. Since the mass is in gram, I have the density also in gram per centimeter cube. And volume is mass by density. Yeah. So last chapter we saw that density is mass divided by volume, wasn't it? Yep. Density is mass divided by volume. When you cross multiply or rearrange, you get volume as mass by density. When you do the math, you get the volume of the piece of iron. Okay. B part. What mass of fluid does it displace? That's easy. That is the mass of fluid it displaces. How do we know? Because the mass of fluid it displaces must be equal to the loss of mass. Let me say it again. Whatever is the apparent loss of mass, that should be equal to the mass of fluid displaced. So we got that. Now you have to find the density of the fluid. See, there's confusion sometimes for students here because there is a solid and a fluid. So be careful. Now we're talking about the fluid. Do we know the mass of the fluid displaced? Yes, we do. Do we know the volume of the fluid? Yep, it should be the same as the volume of the solid. Not always, but in this case. Why? Because it's submerged. So if a solid is completely immersed or submerged, then the volume of the solid must be equal to the volume of fluid displaced. If only half of it is submerged, then the volume of fluid displaced is half of the volume of the solid. All right, going back to this case, because it's completely submerged, we have the volumes to be the same, so now it's easy to find the density of the fluid. Divide 158 by 200 and you get 0.79 gram per centimeter cube. All right, and identify the most likely fluid using the table I did. It's ethyl alcohol. That is the fluid. All right, I already did speak about flotation. You can see that a sponge floats in water, a piece of wood floats in water, but you can see the difference. The sponge floats with just a tiny part underwater, see? But the wood floats with more submerged. Metal cannot float. So the important idea is to understand that this piece of wood or the sponge will go down into the liquid until it balances its own weight. So that means it'll go down into the liquid, and as it goes more and more down, you know that the buoyant force increases, and when the buoyant force acting up becomes equal to the weight acting down, it stops going down. That is true for any solid in any fluid. Now, even if all of it goes down, if it's not able to get a buoyant force equal to its weight, then it keeps going down. So an object floats in a liquid if its weight is balanced by the buoyant force. That is the end, and here are a few more problems worked out. What pressure is exerted by the tip of a nail struck with a force of 20,000 Newton? Assume the tip is a 1.5 millimeter radius circle. Okay, so to find the pressure, we need the force and the area. The force is given and the area is pi r squared. The thing is, this is in millimeters. How do you change it in a meter? You either divide it by 1,000, because 1,000 millimeters make a meter, or multiply it with 10 to the negative 3. Same thing. So which is what I've done, but square it. Again, remember to square both this and this. Now when you square this, it becomes 10 to the negative 6. And then I squared this and multiplied it with pi. I got that. So once you have the force and the area, divide them. And be careful. You can either leave the answer like that, it doesn't matter. But I always like to put it in the standard form. So what I did is 1, 2, 3 places to the left. So I increased this by 3. That is the answer. That's a huge pressure, you may have noticed. That's why we are able to drive nails into wood. The aorta is 1.00 centimeter in radius, and the average speed of blood in the aorta is 30 centimeter per second in a normal resting adult. Calculate the blood flow rate in cubic centimeters per second and liters per minute. Okay, so you have the radius of the aorta and you have the speed in centimeter per second. We are asked to find the blood flow rate. That means we have to find the quantity of blood flowing, means the volume flowing. Okay, how much volume? So Q represents the volume flowing in a second. Always remember that's in a second. And to get that, all you got to do is multiply the speed or the velocity with the area. Now we've done the area many times. It's pi r squared, and I'm keeping it in centimeters, so you get pi centimeter square. I just left it as pi because 1 squared is 1. And we are able to do that again to be consistent with units. Speed is given in centimeter per second. So now if you multiply centimeter and centimeter squared, you get centimeter cubed. So you get 30 times pi. That is the volume flowing in 1 second. But they want the answer in cubic centimeter cube per second. That is there. I mean centimeter cube per second is already there if you put the value of pi. To change it into liters per minute, you got to do 2 things. 60 seconds is 1 minute. 1 liter is 1,000 centimeter cube. Yep, you got to know that. 1 liter is 1,000 centimeter cube. And so when you do the math, you get 5.65 liters flowing per minute. This is real life. This is all calculations we do are real life calculations. It's not made up numbers. So 5.65 liters of blood is flowing per minute through an adult, provided the adult is at rest. And when you have activity, of course, the rate increases. Okay, that should make sense. And that is the end of this chapter. Again, for this chapter, I am going to work out extra problems, but there won't be a video. It'll just be notes, and you should be able to understand. Right? Listen to the video properly. Watch it, understand it. If you have any questions, let me know. Thank you.